Okay, next we will look at an alternative definition of zeros of order m. Here, theorem says let a function f be an analytic at a point g0. The following statements are equivalent. A. F has a zero of order m at g0. B. There is a function g which is analytic and non-zero at g0 such that f of g is equal to g negative g0 to the power of m times g of g. To prove this theorem, we need to consider both directions and this. Both part of the proof makes use of the fact in section 62 that if a function is analytic at a point g0, then it must have a Taylor series representation in powers of g negative g0, which is valid throughout a neighborhood. Absolute value of g negative g0 is less than epsilon of g0. Okay, we use this fact. First, we proved in a forward direction, which means statement A implies statement B. So we first assume that f has a zero of order m at g0. This is assumption. Because the analyticity of f at g0 and the fact that conditions 1 hold here in some neighborhood, absolute value of g negative g0 is less than epsilon. So we have a Taylor series for f of g as this. Here must be careful. The starting index is m. So every term is 0. Yeah, the order is less than m. The degree is less than m here. Yeah, here because we start with the index m. So with this general formula, then we get this and this and this. Okay, just insert m in the place of m here. Then we get this and m plus 1 next. And next we consider m plus 2. Then we get this. Yeah, keep going. Then we've factored this expression by two parts. The first is g negative g0 to the power of m, and second is this. And we are going to denote this part by the function g of g. Then we get this. Okay. So consequently, f of g has the form, okay, shown in the statement B here. Look at statement B is that there is a function g which is analytic and non-zero at g0, such that f of g is equal to g negative g0 to the power of m times g of g. Okay, let us just check it. Yeah, these conditions hold with this expression here. First, it is obvious to see that the function g is analytic because this is power series. And then next, to check this condition, non-zero at G naught, here, we insert G naught, in the place of G, then we get this. Okay. Here, this is the convergence of this last series here. When G negative G naught, the absolute value of G negative G naught is less than epsilon, that G is analytic in the neighborhood and at G naught, and also G of G naught, G of G naught is here. If we insert G naught in the place of G, then this term is 0 and this term is 0, so we get this. M's derivative of f at G naught divided by m factorial is not equal to G, because the assumption is that f has a 0 over order m at G naught. So we complete the proof of this theorem for the forward direction. Next, we are going to prove the backward direction. There is B implies statement B implies statement B A. So we just assume that there is a function G which is analytic and non-zero at G naught, such that f of G is expressed by this formula: G negative G naught to the power of m times G of G. Then we will show that the statement A holds. Since here G is analytic, so it has a Taylor series representation, like this. G of G is equal to G of G naught plus G prime of G naught divided by 1 factorial times G negative G naught plus G double prime of G naught divided by 2 factorials times G negative G naught to the squared to the power of 2. And in some neighborhood, absolute value of G negative G naught is less than epsilon of G naught. Expression 1 thus takes the form here. We replace this representation by G of G, then we get this, where absolute value of G negative G naught is less than epsilon. Since this is actually a Taylor series expansion for the function f of G, according to theorem 1 in section 72, it follows that the terms with a degree k, which is less than m, are all zeros. So we get this result, and that the m's derivative of f of G naught is equal to m factorial times G of G naught, which is not equal to 0, because G of G naught is not non-zero, is not equal to 0, which is non-zero. So it's not equal to 0. Okay. When we compute this f, m's derivative of f of g naught, then from this expansion, we get this m factorial times g of g naught. Okay. So m's derivative of f at g naught, the other terms goes to 0, and we get this term only here, which is non-zero. So the theorem, the proof of theorem, completed.